step back into a world where the continents were not separate entities, but one massive landmass, Pangaea. This ancient supercontinent, which existed eons ago, has long been a subject of fascination and curiosity. But what did it indeed look like? Join us as we delve into the past and uncover the secrets of this mysterious continent and how it shaped the world we know today. Travel back in time to a world where the continents were not separate, but united as one great landmass, Pangaea. Imagine a world where the boundaries we know today didn't exist. The land was connected, and the ocean was one vast expanse. This supercontinent, Pangaea, was surrounded by a global sea called Panthalasus and was fully formed during the early Permian epoch around 299 million years ago. But this land of unity didn't last forever, as Pangaea began to break apart about 200 million years ago, eventually forming the continents we know today and the Atlantic and Indian Oceans. German meteorologist Alfred Wegener first proposed the existence of Pangaea in 1912, and its name was derived from the Greek word Pangaea, meaning all the earth. At the same time, Wegener's theory was met with skepticism. Today, we have ample evidence, including matching rock formations and fossils found on different continents, to support the existence of Pangaea. Imagine a world where the landmasses constantly shifted, coming together to form Pangaea. The Devonian period saw the merger of paleocontinents Laurentia and Baltica, along with smaller microcontinents, forming Euramerica. The Permian period saw Gondwana's northwestern coast colliding and merging with southern America. The Permian period saw Gondwana's northwestern coast colliding and merging with southern Euramerica. The final component was added in the early Permian, with the Angaran craton of Siberia fusing with the combined landmass, completing the formation of Pangaea. The formation of Pangaea, the supercontinent that would eventually become the single landmass on Earth, was begun during the Devonian period, which lasted from 419.2 million to 358.9 million years ago. During this time, the paleocontinents of Laurentia and Baltica, composed of the North American and Eastern European craton, were brought together with several smaller microcontinents to form Euramerica, marking the first step in the formation of Pangaea. A gradual process that took millions of years, the assembly of Pangaea was shaped by the movements of tectonic plates and driven by powerful forces within the Earth's crust. The collision of these ancient landmasses resulted in the formation of mountain ranges, the closing of oceanic basins, and the creation of new land bridges. A time of great change and upheaval, this period shaped the planet as it is known today and is a fascinating subject for scientists to study and understand. As the ages rolled by and the Permian period dawned, spanning a remarkable duration of 298.9 million to 252.2 million years ago, a colossal event occurred that would shape the face of Earth forever. The ancient continent of Gondwana, a vast landmass teeming with diverse forms of life, collided with the southern regions of Euramerica in a massive tectonic shift. This cataclysmic event gave birth to an even more enormous landmass, one that would come to be known as Pangaea. However, the formation of Pangaea still needed to be completed. It was still a work in progress as the forces of nature continued to shape and mold the supercontinent, carving out mountains, shaping coastlines, and forming new seas. In the middle of the early Permian, the Angaran craton of Siberia fused with the combined landmass, completing the assembly of Pangaea. This final addition solidified Pangaea as a single, massive supercontinent that would dominate the Earth's surface for millions of years, creating a unique environment for the evolution and adaptation of life. Pangaea was the largest and most extensive landmass in the history of the Earth, and its formation was a gradual process spanning millions of years. Pangaea was a truly awe-inspiring sight to behold, a supercontinent unlike any other that has existed on Earth. The bulk of its mass stretched between the northern and southern polar regions, with a distinctive C-shaped curve that was truly mesmerizing. The eastern edge of this massive landmass was defined by an embayment known as the Tethys Sea or Tethys Ocean. This sea was an integral part of Pangea's formation, and its evolution over time is a fascinating story. During Pangea's initial assembly phase, the Paleotethys Ocean came into existence. This ancient ocean was a vast body of water that separated the northern and southern parts of the supercontinent. As Pangea continued to form and evolve, the Paleotethys Ocean slowly began to change. The continent, known as the Siberian superterrane, detached from northern Gondwana and rotated northward. This movement caused the ocean to be replaced by the Neotethys Ocean. The Neotethys Ocean was a new and different ocean from Paleotethys. The Siberian continent's movement significantly impacted the ocean's shape and size. The Neotethys Ocean was smaller and shallower than its predecessor, and its formation marked a significant change in Pangea's geology. The Siberian superterrane's rotation also had a profound effect on the climate and ecosystems of Pangea. The movement of the continent caused the ocean currents to change, which in turn affected the weather patterns and the distribution of plant and animal life. Pangea was not the only continental landmass that existed during the Mesozoic era. On the periphery of this supercontinent was a smaller one, known as Cathasia. It stretched beyond the eastern edge of Angara and comprised the landmasses that make up North and South China today. This continent was situated within the western Panthalassic Ocean and at the east end of the Paleotethys Ocean. The ocean surrounding Cathasia was not just water. It was also home to scattered fragments of continental crust, known as microcontinents, basaltic volcanic island arcs, oceanic plateaus, and trenches. As time passed, these island arcs and other isolated landmasses were eventually welded onto the margins of Pangea, forming accreted terrains or landmasses that collided with the supercontinent. The movement of these landmasses and the collision with Pangea profoundly affected the geology of the supercontinent. The collision of these terrains with Pangea created mountains, and the movement of the continents caused the formation of rift valleys and other geological features. The formation of Pangea was not just a mere geographical shift. It had a profound effect on the Earth's climate. As the various large landmasses came together to form the supercontinent, it led to dry climates in the tropical regions during the Permian times. As seaways closed, warm ocean currents were redirected towards higher latitudes, and cool water upwelling developed along Pangea's west coast. The collision of the continents also led to massive mountain-building events, known as orogenies, that strongly influenced local and regional climates. The newly formed mountain ranges disrupted east-west atmospheric flow in the temperate and higher latitudes, diverting warm marine air into higher latitudes. The coming together of the various land masses to form Pangea was a game-changer for the Earth, leading to extinction events near the end of the Permian period. Several factors, including the elimination of several shallow-water marine basins, changes in the ocean circulation patterns and regional climates, and rising water temperatures in shallow areas beyond the tolerance limits of many organisms, caused these events. Paleontologists have theorized the collision of the continents caused the elimination of shallow-water marine basins, which were the primary habitat of most marine invertebrates. Pangea's north-south orientation also altered the flow of ocean currents, which in turn changed regional climates. Additionally, by the end of the Permian period, the landmasses prevented cooler waters near the poles from entering the Paleotethys and Neotethys basins, thereby raising water temperatures in shallow areas above the tolerance levels of many organisms. The theory of plate tectonics has solved the mystery of how Pangea broke apart, which offers a more comprehensive explanation than the outdated concept of continental drift. According to plate tectonics, Earth's outer shell, known as the lithosphere, is made up of large, rigid plates that move apart at oceanic ridges, coming together at subduction zones, or slide past each other along fault lines. The pattern of seafloor spreading reveals that Pangea did not break apart in one single event, but instead fragmented in stages. The theory of plate tectonics also suggests that the continents have joined and separated multiple times throughout Earth's geologic history. The breakup of Pangaea was not just a geographical shift, it also led to the formation of the oceans we know today. The process began around 180 million years ago, creating the Central Atlantic Ocean between Africa and North America, and the Southwestern Indian Ocean between Africa and Antarctica. As the continents continued to separate, the South Atlantic Ocean opened about 140 million years ago as Africa and South America parted ways. At the same time, India was breaking apart from Antarctica and Australia, creating the Central Indian Ocean. The separation process continued around 80 million years ago. North America and Europe split. Australia started to drift away from Antarctica, and India broke away from Madagascar. India eventually collided with Eurasia about 50 million years ago, forming the majestic Himalayas. Throughout the Earth's long history, several supercontinents have been similar to Pangaea. The oldest of these supercontinents is called Rodinia, which formed around 1 billion years ago during the Precambrian era. Another Pangaea-like supercontinent, Pangaea, was assembled 600 million years ago at the end of the Precambrian era. The plate tectonics that formed these supercontinents are still at work, and the present-day plate motions are bringing the continents together again. Africa has begun to collide with southern Europe, and the Australian plate is now colliding with Southeast Asia. Within the next 250 million years, Africa and the Americas will merge with Eurasia to form a supercontinent resembling Pangaea. The process of the episodic assembly of the world's landmasses has been called the supercontinent cycle, or, in honor of Alfred Wegener, the Wegenerian cycle. It's worth noting that this process of assembly and breakup is a recurring pattern in the Earth's history. It has a profound effect on shaping the planet's geology, climate, and evolution of life. This cycle of supercontinent formation and breakup is important for understanding the Earth's past and has implications for the future. The ongoing collision of continents will create new mountain ranges, and the closing of oceanic basins will lead to changes in oceanic currents and climate patterns. The movement of the continents also plays a crucial role in the evolution of life on Earth, as it can lead to the isolation and divergence of species and the mixing of different biotic regions. The next supercontinent will be an exciting opportunity for scientists to study these processes and gain a deeper understanding of the Earth's history and dynamics. The formation of Pangaea was a grand and awe-inspiring event that occurred millions of years ago. It was a slow and gradual process, shaped by the powerful forces of tectonics, erosion, and the movement of the Earth's crust. This massive supercontinent brought together different regions, climates, and fauna, creating a unique and diverse ecosystem and shaping the course of life on Earth for many years. The formation of Pangaea was a pivotal moment in the Earth's history. Even though it broke apart, it left behind a lasting legacy that can still be seen today in the form of continents, mountains, and oceans that we know today. As we look back on the formation of Pangaea, we are reminded of our planet's powerful and ever-changing nature and the importance of understanding and appreciating its forces. Here we come to the end of our journey through the ancient world of Pangaea. As we reflect on the significance of plate tectonics and the assembly of the continents, we want to hear from you. Leave us a comment below and let us know what you found most interesting about the supercontinent Pangaea. Remember to like and subscribe to our channel to stay up to date on the latest in Earth science and mysteries of the past. Thank you for joining us on this journey, and we'll see you in our next video.